Okay. So we consider an orthonormal basis for the n-dimensional complex Euclidean space over n-dimensional real Euclidean space N here. All right, and this is an orthonormal basis if only if that Ui, Uj, when you take the inner product, you get delta Ij. Okay, so as we know, the definition of the delta function is that it is 1 if I equal to j and 0 if I not equal to j. Okay, for or. Right, so you have, this is the economic condition. And so that if you represent this inner product by using matrix multiplication, you have this one. Okay, so the Hermitian transpose, the Hermitian of Uj, and multiply with Ui, okay, give you the Ij. All right, and then this relationship can be written into a matrix equation. Okay, so here, this is U1H, U2H, up to UNH. And here you have U1, U2, up to UN. Okay. So you pile up the row vectors into, so row by row here, into a matrix. And you pile up the column vectors UI into a matrix here. And this is equal to, because of the delta Ij, so this is indeed the identity matrix. Okay? So this is indeed identity matrix. Questions? Okay, so if no, then this, we call this is the U matrix. All right, so U matrix is formed by taking its columns as the basis vectors in this orthonormal basis beta B here. Okay, and this one actually is the Hermitian of U. Okay, this is Hermitian of U here, and this is the identity n times n. All right, where U is equal to U1, U2, and the UN. Okay, so you have a matrix U such that the U Hermitian multiplied with U itself equal to the identity matrix. And this is exactly equal to okay, by the inverse matrix theorem in chapter 3. Okay, so you have that. Okay, so all these are if a non-linear condition. So you have an orthonormal basis for the Euclidean space. If and only if you form a matrix U by using the basis vector together, then this matrix has this relationship. Okay, has this relationship. Right. So this kind of matrix, are special. All right. So we give a definition. All right. So a complex square matrix right, U is called unitary, right? If we have this relation, okay? So maybe I will, because I use the notation n times n matrix, okay? So a complex n times n matrix is called unitary, if we have that. And a real n times n matrix, U, is called orthogonal. If U transpose equal to U transpose U equal to n times n. Because for real matrix, permission transpose is equal to just the transpose. So they are called orthogonal or unitary. Okay? So you can see that U is a complex unitary matrix. All right, so we see that U is a complex unitary matrix n times n matrix. If and only if, so right, so U, and it has n columns. It's a complex unitary n times matrix if only if its columns, it's an orthonormal basis for Cn, and similarly U1, U2, Un is a real orthogonal n times n matrix if and only if U1, U2, Un is an orthonormal basis for Rn. So they are all orthonormal. Maybe I'll also normal. So they are all orthonormal basis. But for real case, just orthogonal is enough. And for unitary case, you can just omit the complex, because whenever you talk about unitary, you understand that you are talking about a complex case. Okay. But for orthogonal, you have to put real, because it's possible for a complex matrix that it's possible for a complex matrix that this is true, okay, but not unitary. It's possible. Okay, so we have all this information here. All right, so now we will talk about the projection. Right? We talk about projection in real Euclidean space. Now we will transfer that notion of projection, because projection is a geometrical notion, into general inner product space. Okay? So now, the orthogonal projection of a vector, so of x in an of a vector x in an inner product space V, okay, onto a non-zero vector y in V, all right? All right, it's a vector, right, and we denote it as PROJ YX. It's a vector in the span of Y, okay, so that the projection of a vector X will be parallel to this non-zero vector Y. Okay, so in span means that because all the vector in the span of Y would be parallel to the vector Y. Right? So parallelism is a geometric concept. Okay, and this is actually any scalar, okay, such that x minus the projection onto, right? So this vector, so we have, so this is y vector, and we have x vector here, and the projection, this projection is PROJ Y, right? So the projection of x onto the non-zero vector y is this one, and we say that this projection is orthogonal projection. We mean that we have so that the difference. So this difference is x minus the projection should be orthogonal to y. Okay, so should orthogonal to y, so that by our definition, two vectors in a general inner product space to be orthogonal if and only if their inner product is 0. Okay, so this is definition about orthogonal projection. It's that a concept we transferred from the orthogonal projection in the real Euclidean space. Okay, so in parallel we give this one. Okay, and so that we will have a theorem to really compute the projection, the orthogonal projection, right? So the 7.1.5 PROJ Y X is equal to the inner product of X and Y and Y. Okay? So this is our result. That from the definition, this vector, because this vector, as we know, should be in the span of Y. Okay? And this is exactly that. And remember, because in here in definition Y is non-zero, so that the denominator is just the square of the length of y here. Okay. All right. So now we have proof here. All right. So things, by definition, we know the orthogonal projection, all right, is in the span of the y vector. All right. So the projection should be equal to alpha y for some scalar. Right? So from the definition. So in this definition, there are two requirements for the orthogonal projection. One is that this orthogonal projection should be in this span. The second is that this difference vector should be orthogonal to y. Okay, from this diagram here. Okay, and the things, the second requirement is 0, right? So we have, okay, so we have that the projection is 0. So this implies that minus the x, y minus alpha is 0. So this is implies if only alpha is equal to okay. So immediately we find alpha. So the projection, so the orthogonal projection of x onto the non-zero vector y is equal to this vector. Right. Okay, as we specify there. Questions? Okay, a remark here. If y is normalized, i.e., if the length of y is equal to 1, then the projection of x onto this normalized vector y is equal to y. Okay, because the denominator is equal to 1 here. Okay, so this is a projection onto a vector. And we need a concept about projection. So suppose we have a vector inner product space V here. Okay, and here we have a subspace W here. Okay, and this is our zero vector origin. Suppose this is our zero vector. Okay. And if we have a vector x here, we want to know we want to define a second projection of x onto this subspace. Okay, so that it's reasonable to have, if to want to have a second projection, right? So that so we want that so this one, okay, and so the orthogonal projection of x onto the subspace W should be in this subspace. Okay, this is reasonable, right? And we also require that the difference. So Okay, so suppose we denote this sample as PROJ to W of X. Okay. So now this vector is X minus PROJ WX. So this vector, to say that is an orthogonal projection, is that this vector should orthogonal to any vector, okay, in the W, okay, they should orthogonal to. All right, so that if W a subspace of an inner product space, V, all right, and the X in V. Okay, so a proper definition of the orthogonal projection PROJ WX of X onto W, right? So this vector should have the following two properties. Okay, so it should have the following two properties from this diagram. So the first property is should this orthogonal projection should be in the subspace. So because we want to project into the subspace. The second thing is that the difference, right, of X and its orthogonal projection should orthogonal to every vector Y in the subspace. All right, so this should be a proper definition for that. Okay. Now, to justify this definition works means that we're defined, because in the definition here, in this definition, we immediately give you a theorem how to find this orthogonal projection of X onto a non-zero vector Y, right? So a definition, and then you have a theorem to show you how to compute this vector, this orthogonal projection. So similarly, if this is a proper definition, okay, with this, then we should be able to give you a theorem like here, right? But unfortunately, this is generally not true. Okay? I mean generally not true. But in our case, we will see we are able to find orthogonal projection immediately. Okay. All right. So I just give you a warning that even though this definition is really proper, okay, it's so give you a geometrical intuition, but you may not be able to compute it. For general inner product space to general subspace. Okay. All right. So now I will give you partial answer first. Okay. I will give partial answer. First lemma. Okay. Now, W, a subspace. Okay. So maybe I don't repeat it to save time. All right. So I just say W, they are all the same. Okay. All right. If I just say if they are two vectors Z and the Z prime in the subspace such that, so suppose we have two such that X Z, so such that X minus Z is orthogonal to OY minus Z and X minus Z prime are orthogonal to all vectors in W then Z must be equal to Z prime. So the theorem gives us that if such a vector exists, means that if there is a vector satisfy these two properties, then this vector must be unique. So existence implies uniqueness. Even though we don't know whether, we haven't settled the existence problem yet, but if we have one vector satisfying these two properties. So if we have a vector called Z, right? So Z is in W, and the X minus Z is orthogonal to every vector in W, right? And if we have another Z prime, okay, Z prime is also in W, and the Z prime, X minus Z prime is also orthogonal to every vector in W. Then this Z and Z prime must be equal. Okay, so at first we can give you the partial answer, and the proof is quite straightforward. Now, since all right, so they are 0. Okay, for all y. Right? So because we say that they are all orthogonal to y, so that X minus Z minus X minus Z prime. So maybe I use Z prime as Z, and the y must be 0. Okay? For all y in W. But the difference here is Z minus Z prime. Okay, so Z minus Z prime is orthogonal to every vector in W. All right, so in particular, so we let y to be Z minus Z prime, which must be in W. Why? Because that Z and Z prime is in W, and W is a subspace already. All right. So by dating this one, so we have all right. So we have that. So if we let y to be Z minus Z prime, then this is 0. So this implies that Z minus Z prime is the 0 vector. So this implies that Z is equal to Z prime. Okay? So immediately we know if there are two vectors satisfying these two properties. All right, so lemma 7.1.8 implies that the orthogonal projection, if it exists, must be unique. Okay, so we settle first that if the orthogonal projection of a vector onto a subspace exists, then it must be unique. Another important way to identify the existence of orthogonal projection will be specified in the following way. Okay, so if projection, so if the orthogonal projection of a vector x onto a subspace W exists. All right. So if this exists for an x in the inner product space V, then we have that this vector, okay, this vector has the minimum value for all the vector W, and so that y. So the length of this vector for arbitrary y in W, okay, so x minus y has length greater than or equal to the length of this vector, this also. Okay. And this concept, you can see that we see this property from Euclidean geometry already. And you see that the same concept can be appeared in general inner product space. Okay, so if the orthogonal projection of X onto a subspace W exists, then it has this minimum property. Okay, and also the orthogonal projection of X onto W is the unique vector in W, right, having this property, this minimum property. Okay? So orthogonal projection has this minimum property, and this is the unique one to have minimum property. And conversely, if there exists a vector z in W such that this z has the minimum property right? So suppose there is a vector in W, okay, having this minimum property. Then this Z is the orthogonal projection of X onto W. So the minimum property. This minimum property is if an orderable condition for the existence of a orthogonal projection. Okay? So that means that if there is no orthogonal projection of X onto W, then there is no vector Z in W achieve the minimum. No. There is no minimum property at all. Okay? There is no property at all. And this happened if the W, the subspace is not finite dimensional. Okay? I will say that again. Anyway, so orthogonal projection, this concept is equivalent to the minimum properties we encountered in Euclidean geometry. Okay, so now we give a proof for that. All right, so first we assume that the projection, orthogonal projection, exists for an X in V. Okay? Now we will prove that it will. So now for all Y in W, okay, we compute the square of the length of the difference here. So we compute the length of this green vector here. Okay? For arbitrary vector Y in the subspace. And this one can be, so we will minus 1, but minus the projection, the orthogonal projection, because we assume the orthogonal projection exists. Okay, and projection, and plus 1 square, yeah. All right, and by definition, we know that we know this one, this vector is in W, because Y is in W, and the orthogonal projection of X onto W is also in W. So this is a vector in W, and this vector is this red vector. And by definition, okay, that it satisfies this property. So that this difference vector are orthogonal to any vectors in W. So we have we can apply the Pythagorean theorem, right? So by Pythagorean theorem, right? So that so this is by Pythagorean theorem. Okay, so we have this one, and so this is greater than or equal to minus projection. Okay. Right, because this term is non-negative. Okay, and okay, so So they are orthogonal to each other. We know that they are orthogonal. Okay? They are orthogonal to each other. So we have this one. And any questions? Do you have any questions that these two vectors are orthogonal to each other? No. Okay? Okay, because here, right, the difference should orthogonal to any vectors in W. Okay, and this vector is in W. Okay. All right, so we can apply the Pythagorean theorem. So we have lower bound. Okay? So we have the lower bound here. So this is equal to the minimum for all possible cases. And the minimum achieved and the equality holds. So that the equality if and only if that the y is equal to projection. So this says that projection, the orthogonal projection is the unique vector has this minimum property. Okay. So minimum property means that equality holds. Okay. So we prove. Okay. Now suppose that. So now assume there exists a vector z in W such that x minus z is equal to the minimum of y. Okay, and we want to show that z is the projection of x onto W. Means that we want to show that it satisfies these two properties. But the first one already satisfied. Why? Because here we say z is in W, right? So z is the W. So the only thing left is to show x minus z is orthogonal to every vector y in W. Okay, so this is the only thing left to show. Okay, all right, and so we come up here. Okay, so again, we know this is right. So if we add the arbitrary vector y in W, right, we have this inequality because this is the minimum by the minimum property there. Okay, so when we add a y here, the reason is that this is equal to x minus, right? And the z minus y is in W. Because z is in W, y is also in W in the subspace. So the difference is also in W. Okay? And we take the square. When we take the square, now, so we have, so we can do we use the algebraic property. Okay, so we can expand this inner product into, so this is z square plus x minus z and y plus y x minus z plus y square. It's here. And our goal is to prove this inner product is 0 for any y. Okay? Our proof is that. So it seems hard, right? Okay. But first of all, you can cancel them. So you can see that you see that so this is combine them together. So this is the 2 times the real part of x minus z and y. Okay, so that when we cancel them and we move this to the left hand side, so we have minus y square is less than equal to 2 times the real part of. Okay, so we have this functional relationship for all y in W. We have that. Okay? All right, so we suppose our purpose is to show this inner product is 0, right? So suppose that there exists a y0 in W such that y0 not equal to 0. Suppose we have, okay? Suppose we have a vector in the subspace such that this inner product is not 0. Okay? All right, and so let's goes to a plus ib not equal to 0. Well, a is the real part of and b is the imaginary part of the inner product. Okay, so we express the inner product in general is a complex number, and we suppose that this is non-zero. Okay, non-zero. Okay, so there are several cases to consider. Okay, so if a, right, is negative, right? Suppose a is negative. So a is negative. Okay, and so if a is negative, then for all gamma greater than 0, so we put a parameter gamma which is positive. Then we see that we see that that the 0 would be greater than 2 real part of. So we have. Oh, by the way, we were for simplicity we just divide the 2 into here. All right, so gamma, because this is real part. The real part is a negative, so that gamma times the real part is also negative, so it's less than 0. So the real part of okay, so we have this one, right? Is that okay? So when we multiply the real part by a positive number, still a negative number, right? So this is correct. But what is that? This is the real part of x minus z. Oh, I'm sorry, y0. And we can absorb gamma into here. Is that okay? Now, we apply this formula because gamma y0 is also in W. So this is greater than or equal to minus 1/2 and gamma y0 square. Okay, and so what is this? This is equal to gamma square or square. Because it's square, we can move it out, right? So this is gamma square here. Okay? So we have this inequality here. Now dividing gamma, right? Because gamma is positive, so we can divide them. We have that 0 greater than real. So we will have anyway real part of here, right? And greater than or equal to gamma square. Is that okay? Right? And so this is true for all gamma greater than 0. Okay? So we have such inequality. Now, by letting gamma goes to 0. So by letting gamma goes to 0, so we have 0 greater than real part of x, z, y0, I'm sorry. Right? It's greater than or equal to 0. So 0 is greater than 0. No, 0 is greater than 0 because of this inequality. So that this is a contradiction. Okay? So this is a contradiction. So we get to a contradiction. All right? So we get a contradiction because we assume that A is negative. Okay. Now, so now if this way nowhere this way is incorrect. So if A is positive, then okay. So if the real part is positive, and then we consider minus y0 instead of y0. Okay, so now we consider it, and so that again the real part of x minus z y minus y0, okay, and multiplied with gamma is also negative. Okay, so if minus y0 here, so this real part becomes to negative, and gamma is positive again. Okay, so that this is again a real part of minus gamma y0, and this is 1 minus gamma y0 square, and this is gamma square again, we have that. We have the same situation. Okay, and this is for all gamma greater than 0. Okay, and again, by letting gamma goes to 0, so we have 0 greater than, and so we divide. So if we divide thing gamma and letting gamma goes to 0. So we have 0 goes to real part. We'll go to the limit gamma goes to 0, which is 0. Again, a contradiction. All right, so this is the second contradiction. All right, so thus A, the real part of the x minus 0, y 0 must be 0. Okay? Must be 0. Okay? And now the imaginary part. So if, again, so now we would use the same strategies. If B, imaginary part of, okay, if the imaginary part is negative, our positive, okay, we consider I, y 0 or minus I, y 0 instead of y 0. Okay. So if this imaginary part is negative, okay, yep. So we consider I, y 0, and if positive, we consider minus I, y 0. Right? So, and we do the similar argument here. We can do the similar argument. Okay. Or maybe I will do it. We consider say the I, y 0 instead of y, and then the real part of x minus z, I, y 0. Okay, this is the real part of minus I and x, y 0. Okay, and which is the real part minus I times IB. Okay, because that the real part of this inner product is 0, so it is purely imaginary. Okay, so this inner product is IB, and this is equal to equal to B. Okay, so this is, in this case, so the real part is negative. And so for all gamma greater than 0, gamma of real part IY0. Okay, so this is the real part of I gamma Y0. Okay, and this is greater than 1/2 of the I gamma Y0 square. And again, gamma square. Okay. Okay, so we get the same inequalities. And then we divide. So once again, dividing okay, so dividing gamma and letting gamma goes to 0, we have 0 is greater than real part of the I Y0 and greater than or equal to the limit. Once again, a contradiction. Right? And the final case is that, if B is the imaginary part of is positive, we consider minus IY0 instead of Y0, and reach to a contradiction. All right, so starting with here, that this inner product is non-zero, and but we check everything that A must be 0 and B must be 0. Okay, so we consider all the possible cases and get to contradiction. So that means that this assumption is incorrect. Right? So we conclude that x minus z is 0 for all y as in W. Right. So by lemma, 7.1.8, the previous lemma here, that z is equal to the orthogonal projection of x onto W, because it's unique. So existence implies unique. Okay. Any questions? Okay, so let's take a 5 minutes break up to 11:20. Okay, a correction here. Thank you, two lovely students pointing out the errors here. That the y vector should draw from the origin to here, because that we pointed to regarded as the position vector. So we should draw the y vector from 0 vector here. Okay, so please correct this diagram. Yeah, I'm sorry for the mistakes. Yeah. Fortunately, we can correct it before the end of the class. Okay. All right. So we just prove that the minimality minimum property is equivalent to the orthogonality property. Okay. So that even though we are now considering general inner product space, but the geometric concept is actually exactly the same as we have in the Euclidean geometry more than 2,000 years ago. Okay, so it's very old, okay, but useful again. Right. All right, so now we answer our questions that orthogonal projection of a vector onto a subspace exists in a case which would be sufficient enough for us in this class. All right, so I just write down. So we next show that the existence of orthogonal projection is guaranteed. Okay, when W is finite dimensional. Okay, W is finite dimensional. Okay, so to ease our discussion, okay, so we let, so that we say B basis U1, U2, UN, and also normal basis for an n-dimensional subspace. Okay, so W is n-dimensional subspace, and we take an orthonormal basis. You may argue that, well, how do you know that a finite dimensional vector space has an orthonormal basis? Well, this will be answered. The answer is yes, but we will discuss that in the next section by providing a procedure, okay, to find an orthonormal basis from a basis for an inner product, finite dimensional inner product space. Okay. Okay. So, so suppose we have an orthonormal basis here. All right, and so by the first requirement, okay, by the first requirement, the projective, the orthogonal projection should be in W. Onto W should be in W. Okay, so that this orthogonal projection can be written as a linear combination, okay, for some scalars alpha 1 up to alpha n. Okay, so we know that to search for an orthogonal projection, okay, of X onto W is just to show that we have a linear combination of this basis vectors here, right? And also by the second requirement. Okay, so please correct the diagram here. Okay, so by the second requirement, all right. So we have that the difference vector of X and its projection is a orthogonal projection onto W. Okay, should be satisfied. And but this is if and only if that UI, yeah, UJ. Okay, I use UJ. Okay, because that this difference vector orthogonal to every vector in W is equivalent to orthogonal to every basis vectors UJ in this basis. All right, and so that we plug into this formula. Okay, we plug into them so that we have X and UJ. X Uj is equal to the summation and the alpha I Ui Uj. Okay, right? So we move this into the right hand side. Okay, and because Ui, because the B is an orthonormal basis, so we know that this inner product is a delta Ij. Okay, and so we have alpha j. So we have alpha j here. So alpha j, the coefficient we find is just equal to, right? So we find the alpha j from the second requirement. Okay, and okay, so now we have a theorem 7.1. Okay, so now we are able to give a definition now. Okay, so definition. Okay, all right. So the orthogonal. The orthogonal projection of X in an inner product space V onto a finite dimensional subspace W, right, of V, right? So the key word is here. We have finite dimension. Okay, I already erased that, but you can compare with our proper definition before. In that case, I didn't specify that W is finite dimension, but in here, to be a definition, right? This orthogonal projection should be computed. All right, so the orthogonal projection of X onto a finite dimensional subspace is a vector. Okay, it's a vector denoted as PROJWX. Is a vector in W such that the difference of this difference vector is orthogonal to every vector in W. Okay, and so now we immediately has the following theorem. Okay, so we have the theorem here, 7.1.E. So beta B U1 U2 UN. All right, so B is B, and also normal basis. And also normal basis for an n-dimensional subspace of an inner product space. You should know that this inner product space may be not finite dimensional. Okay, the V can be arbitrary. The only restriction is that W, the subspace, is finite dimensional. Okay, finite dimensional. All right, so B is there. Then for all X in V, the orthogonal projection of X onto W is actually equal to this formula. So we have a good definition and a good theorem here. If our subspace W is finite dimensional. Okay, so the proof, this follows from the discussion before the previous definition, and by lemma 7.1.8, because lemma 7.1.8 says that if there exists a vector, so we know in here in the discussion we found the coefficient of I. So we have existence, and the lemma give us the uniqueness. Okay, so this is the only one to have. Why is so important? This means that the result is independent of what? The orthonormal basis you select. You may ask, if I use different orthonormal basis and compute, if you use this one, do they the same? And the answer yes, because lemma 7.1.8. So lemma 7.1.8 is very important to give you that once you have one, you have a candidate for the orthogonal projection. Then that candidate, this one is the only one. Okay, this is the only one you have. So that this lemma tells us the suppose this is 7.1, right? That's 7.1. Okay. The summation right? So this vector, all right, this vector in 7.1 is independent of the basis, so normal basis be selected, or we just say chosen. Okay. Okay. So it's very important to tell us that. Questions? And so I also indicate that V may be not finite dimensional. Right? V can be not finite dimensional, but for this theorem to work, that the W, the subset, should be finite dimensional. Okay, so I will put a remark here. PROJWX may not exist when W is not finite dimensional. Okay, so I just give you the warning that if W is not finite dimensional, then the projection of X onto W may not exist. So you have to put condition on such an so-called infinite dimensional subspace. And the condition is called closed, right? But I don't want to dwell get into that subject, okay? Just give the warning here that, okay? So in your later career, if you need to consider projection onto W, which is not finite dimensional, then you have to find a good condition on this infinite dimensional subspace such that the projection exists. Okay. Okay, but for our purpose, because we usually talk about finite dimensional subspace, so well, you have, and that is the one here. Okay, so let us take an example, right? You like example? So suppose we have an orthonormal basis, right, for a k-dimensional subspace W of the Cn. Okay, so in Cn, in the n-dimensional complex Euclidean space, we have a k-dimensional subspace, and we find an orthonormal basis B for W here. Okay, so now then, for all vector in the n-dimensional Euclidean space, all right, the projection of X onto W, all right, by our theorem is this one, I from 1 to K, and the X, you take UI, and the UI here. Okay. Now, since we are considering Euclidean space, as we demonstrated before, inner product can be represented as metric multiplications, right? So in here, I just purposely move the scalar in here, all right? So I just exchange the order. That's fine, because this is scalar, right? So I modify scalar from the right-hand side here, all right? And so this is UI. But what is that? This is UI Hermitian, okay? And X here. All right, and so that and X is not involving the sum, so I will read this one and focus on the sum in the parentheses. And what is that? Very interesting thing. What was that? Well, you can think about this is U1, U2, UK. And the row vector U1H, U2H, UKH, and the X here. Is that okay? So that you list the column vectors in here as a row vector. So this is a row vector of column vectors. And this is the column vector of row vectors. Okay. Here. All right, and with that, this is U, and this is U Hermitian and X here. Okay, so where the U matrix is an n times k matrix. Okay, so that this is n times n matrix. Okay. So you have an n times n matrix, and this n times matrix U multiplied with the Hermitian of the U. Okay, and this matrix U is formed by using the basis vectors as columns. Okay, as columns into that. Okay. Okay, so the projection. So now the projection of vector X in the n-dimensional complex Euclidean space can be obtained by multiplying the X by a matrix. And this matrix, this n by n matrix, is obtained, is the product of U and U Hermitian. And what is U? U is just a matrix constructed by the basis vectors. Okay. Questions? Good. No questions now. Now we will we will explore the concept of orthogonal projections further. Okay? Orthogonal projection is not a good geometric concept. It's also a very important tool in the study of inner product space. Okay, so the first one is that, so suppose X is a subset of vectors in an inner product space. V. So X is just arbitrary subset. All right, and we define this set to be all the vectors in V such that the vector X will be orthogonal to V for all V in S. Okay. So that is, this is actually such that okay. And so this is called the orthogonal complement of X in V. Okay? So you are given a set of vectors. Okay? Now, in the orthogonal complement of X, is contain all vectors which are orthogonal to every vectors in the set. Okay. All right, and so we have a lemma. If T is a bigger set, so if T is bigger, right? Then, if you have bigger set, then the orthogonal complement is smaller. Why? Because that you have more vector to check, right? Right. So obviously this is the case. Well, but if you really need a proof, well, yeah, I can give you a simple proof that X is in the orthogonal complement. X is in orthogonal complement. This implies that X is orthogonal for all V in T. Okay? But T is bigger, so right? So if this is true for all vector in T, then it must be true for all vector in X. So this is implies that X is in S, and we have done. So every element in the T perp, T perp is in S perp. Okay. All right, and this, but there is one, but the S perp, the orthogonal complement of X, is the same as the orthogonal complement of its span. Okay. We know the spanning set of X is bigger than X, of course. So that this is smaller. It seems like smaller. So the proof is that since S is contained in the span of S, right? So the orthogonal complement of the span of S should be contained in S complement by lemma, right? 7.1.b. Okay, so this, of course, this is true. Okay. So we have to prove that every vector should be in here. So okay, so now if x is in the orthogonal complement of x, so that means that right, and so this is saying that okay. Now, so if we so okay, so if we take v1, v2, vn from S, right, and for all scalars, alpha 1, alpha 2, alpha n, and for all n, okay, this is always true, all zeros, right? Because x is orthogonal to every vector in S. And so if you combine them together, right? This is true, right? For all v1 and all scalars. Okay, and this by the conjugate linearity, okay, and the conjugarity for all v1 okay, so we have that. But any such linear combination is a typical vector in the span of X. Okay, so this is okay. So such a linear combination is just a vector in the span of X. Okay, so this implies as X is equal to U for all U in span of X. So this is implies that X is in the orthogonal complement. So starting from here, you get to here. All right, so that S is the S perp is contained in the span S perp. Okay, and then you combine there so that S perp is equal to the span perp. Okay. Questions? Okay, no questions. All right, so the next theorem shows that the orthogonal complement of a set, of a subset, all right, is a subspace, even though S is not just a set only, okay? All right, so the proof is, but to show that, because we have experience in chapter 5, first of all, we have to show the orthogonal complement is a non-empty set, okay? All right, and so we check. So since the 0 vector is orthogonal to every vector, so, right? So that we know, so 0 must be in the orthogonal complement. And the orthogonal complement is non-empty. Okay, so now, first of all, second thing is that we have to show that this set is closed under vector addition and scalar multiplication. Okay, all right, and so we let x, y in the orthogonal complement, and alpha a scalar. Okay, our scalar. Now, since because that xy is in the orthogonal complement of x, so x is orthogonal to v, and y is orthogonal to v for all v in S. Okay? So that we have, now we look at the sum of these two vectors. The sum of these vectors, you know that this is easy. Okay, so this implies that for all v in the x, so this is defined as x plus y is in the orthogonal complement, and also alpha x v so this implies alpha x is also in. So you see that the S perp or the orthogonal complement of x is closed under vector addition as well as scalar multiplication. So it's a subspace. Okay? By theorem 5.1.1 before. Okay. Now here is so you may have question that given a subset X, how do you compute the orthogonal complement? Okay, here is a special case you will encounter, right? Especially for vectors, okay, in Euclidean space. All right, so we recall the null space. All right, so we consider here, all right? So A is M times N matrix. Okay, and the null space we know of A. Okay, it's all the set in F. All right, so the matrix can be real, complex anyway, such that. So the null space is the set of all solutions of the homogeneous linear system. Okay, so we know that. All right, and so we let A, I be the ith row of A. Means A is equal to A1, A2 up to AM, because we have M rows here. All right, so now, so we see A, x equal to 0 vector. Okay. All right, so that means that the AI x is 0 for all I from 1 to m. Okay? So the row vector multiplied with the column vector is 0. All right, now AI is the Hermitian of the Hermitian, because the Hermitian operator inverse itself. Okay? And x here equal to 0 for all. Okay? So now we are able to write down AIH okay, right? So this is 0 for all. Okay, and now, so that this is equal to 0 for all y in the span of A 1h up to A mh. Okay, it's okay. So x is in the null space of A if and only if. So we have long chain, right? So x is in the null space of A if and only if. All right. So if and only if x is in the span is an orthogonal complement of A1h, AMH, orthogonal complement. And you see that so we define the row space of A, take the Hermitian operator, is the y Hermitian for all y in the row space of A. Okay, so row space of A is just a set of vectors, and we take the Hermitian, means that because those of A consists of row vectors, but when we operate it on the Hermitian operator, that becomes two column vectors. Okay, so they becomes column vectors. So this is definition. And so you can see that this is just the span of A1h up to AMH. Okay, so this is span. So we define. You can see that. So finally, okay, so we have a theorem 7.1.8. If A is an M times N matrix, okay, maybe real or complex, then the null space of A is just the orthogonal complement of the Hermitian of the row space of A. Okay? So this is good in Cn or in Rn. They are all always good. All right, so that the theorem, the corresponding theorem in the textbook is not general enough. Why? Because that theorem applies only for real cases. If we want to apply to the, and also it's incorrect because that for real case, you have to put the transpose. You have to put the transpose. Okay, because row vectors are totally different from the column vectors. Even though they are isomorphic to each other, but they are different objects, okay, mathematically. So you have to let the row become two columns by doing the transposition. So you have to take the transpose at least for the real case. But for the complex case, this is not enough. You have to take the complex conjugate to transpose. Okay, so you have to take the Hermitian operator. Okay, so theorem 7.1.8 in the textbook, I would say that is incorrect. Okay, mathematically. Okay, even spiritually is correct, but in mathematical definition, it's incorrect. So you have to put the H there. Okay, the reason I have already shown here. The long chain of if and only if conditions. Yeah. Questions? Okay, and in my lecture notes, I surprised you an example. All right, so please, I have no time to examine the example. I encourage you to read through it. Okay, so all right, so V is an inner product space. W is a finite dimensional subspace of V. Okay, so now the function, the orthogonal projection, we are OJW. Okay, so the function is from V to V. Okay, so the definition is that for X goes to projection of X onto W, and because W is finite dimension, so this is well defined. So actually, PROJW define a function. Okay, for each vector in V, you have a orthogonal projection of X onto W here. Now, so we have now, so the function, okay, is a linear transformation. Okay, a linear operator because it's from V to V, so that it's a linear operator. Operator on V. And its kernel, okay, and with the kernel of this PROJW, which is just the orthogonal complement of W, and the range of this linear operator is the W itself. And furthermore, that if we project, if X is in W, then the projection will be itself. Okay? So if the vector is in the subspace already, then the projection of X onto W is itself. Okay? So this is, of course, this is true. Okay? All right. So the theorem is important is that this function is a linear operator. Okay. And then we know this linear operator has kernel, which is just the orthogonal complement of W. And the range is W itself. Okay. In particular, that if the vector is in the subspace W, then the projection of X onto W is the X itself. You will not change the vector XO. Okay, so the proof, right? Again, you select an orthonormal basis. Okay, so it's an orthonormal basis. Okay, it's an orthonormal basis for W. And of dimension K. Okay, so the subspace is finite dimension, so we suppose that the dimension is K, and B is an orthonormal basis, okay, for the W here. Okay, so now okay, so for all vector xy in V and the alpha beta scalars, okay, so we check right, so we check this, the projection of this linear combination onto W, and by definition, right, so this is by definition here. So by linearity, okay, so we find that immediately. Right, so this is by linearity for the first argument of the inner product. So you see this is alpha, and this is the projection of X plus beta, projection of Y here. Okay, so right, so we have linearity. So that projection is a linear operator. On V. Okay. Now we have to show right. Now X is in the kernel of this linear operator. Right? So X is in the kernel. If and only if the projection is the zero vector. Okay? So if only if so this projection, let me write it down. I from 1 to k is a zero vector. Okay? So this is a zero vector here. But this is if only because UIs are basis vectors. So the basis is linear independent. All right? So this is a linear relation, right? So it's a linear relation on the basis. So this says that x ui must be 0 for all I. Okay. So the reason is that it's linearly independent. Okay. So it's a linear independent state. Okay, and this specify a linear relation. Okay, summation, right? This is coefficient and the vectors. So all the coefficients must be 0. Okay, and if this is true, then x then that okay, so that then x is orthogonal to every vectors in W, and so this implies that V is in the orthogonal complement. Okay, so x is in the kernel if and only if x is in the orthogonal complement of W. All right, so that the kernel of this projection, this orthogonal projection is equal to this one. All right. Okay, and also by definition, we know that the range of the orthogonal projection is in W, because every orthogonal projections of X onto W must be in W. This is by that definition. So the range, right? So the range, because this one must be in W. So the range must be contained in W. All right? And we have to show that the W will also contain in the range. Okay, so to show that for any x in W, we have so that we have x can be written as a linear combination, a unique linear combination of the basis vectors. Yeah, because B is a basis for W. Okay, so we have that. And then, so we have the projection becomes to summation of I from 1 to k x u I ui. So this is by definition. And we move alpha j, uj. Okay, so we do the substitution x by the sum, by the linear combination of uj's. Okay, and so we have a double sum I, j from 1 to k, and we have alpha j here, and we have uj, ui, and ui here. Okay, but this one is equal to delta ji. So this is 1 if I equal to j, and 0 if I not equal to j. So that this becomes 2 I from 1 to k, and the alpha and I, and the ui. Okay, and this is exactly the x itself. Go back to x. So the projection of x, if x is in W, the projection of x onto W is x itself. Okay, so this implies that the W is contained in the range of the projection W. Okay, so finally W is equal to the range of the projection W. And we already show that so we already show that this is true. Okay, and so we have the thing that suppose now V is an n-dimensional inner product space. Okay, and the W a subspace of V. So now consider the inner product space is n-dimensional. Then the dimension of W plus the dimension of the orthogonal complement of W is equal to n, is equal to the dimension of V. Okay, and the proof is simple. So that okay, so we know projection W from V to V is a linear operator on V. Okay, and so we can apply. So by theorem 5.2.17 in chapter 2, we know that the kernel of the projection W plus the range, the nullity. Okay, so the nullity, all right, of the linear operator plus the rank of the projection, okay, is equal to n is equal to the dimension of the domain. Okay, so this then apply to if the linear operator is on a finite dimensional vector space. So we have that. This is one here. But the nullity is actually the dimension of the null space of the projection W. Okay? And the rank is equal to the dimension of the range of the projection W. Okay? But from the previous theorem, all right, that the null space is equal to the orthogonal complement of the W, and the range is equal to the W self. Okay, and so finally, so we have okay. So basically, the theorem is a consequence of our theorem about linear operator in chapter 2, okay, and the theorem 7.1.f. Once we prove that the projection, okay, of onto W, okay, so because this is a linear operator, right? So this would be called the orthogonal projection, right, from V onto W. Okay. So this linear operator is called the orthogonal projection from V onto W. So you can see that V is the domain, the operator, and the W is the subspace it will project onto. Okay. So this is the case we have here. Okay. Okay. Any questions? Okay. So I'll stop here. Okay. So just a little bit. Only one more theorem left. So I will discuss that next Wednesday.